Okay, let me just go through the concept of time here. Now remember, longitude is equal distance, or is angular distance east or west of the prime meridian. Now, keep in mind this, that the Earth's day is 24 hours. So it takes one revolution of its axis, takes 24 hours. Now, think of it this way. If the day has 24 hours, and the Earth rotates 360 degrees on its axis every 24 hours, then if you divide 24 into 360, you get 15. So each hour of time, the Earth rotates 15 degrees. And that led to the discovery of how to measure longitude. It wasn't a scientist that figured this out. It was actually a guy that made watches or clocks. And he was able to make a pocket watch that was highly accurate. The contest was to sail from London to Jamaica. And when you got to Jamaica, calculate the exact longitude, and whoever could do that would win the prize. And if you know that for every hour you sail of celestial time, you travel 15 degrees, so you have one watch that has London time, one watch that has Jamaica time, subtract, multiply by 15, and that will give you your longitude. And that's how the guy did it and ended up winning the prize. But that's how you also set the time zones. Notice that they're not exactly straight lines, and lots of reasons for that. But notice in the U.S. we have Eastern, Central, Mountain, and Pacific where we are. And then you can see Alaska has their own and so forth. But generally, each hour of time represents 15 degrees of longitude. So that's the relationship between time and space. That's how you figure that out, okay? Now, we can represent the Earth on a piece of paper, and that's called a map, or on a computer, or whatever you want. But we have to take the whole Earth and reduce it down in size, and that is scale, the ratio of map units to ground units, which I'll get to in a second. And you can do this in all kinds of different ways. How you do it is called the projection. So the map is just the generalized view. The scale is how much the projection is the process used to change the 3D spherical Earth to a flat map. This is in the book, but again, make sure you know all this. It's important. Scale, again, just the ratio of distance on the map to that in the real world. It can be a fraction, it can be what we call a graphic scale or a written scale, and I'll show you that in a second. So, 1-to-1 would mean that an inch on the map represents an inch on the ground. But think of it, it would be really impractical because your map would be the same size as whatever it was you were trying to map. So if you wanted to map the campus, well, the map would be the size of the campus. So you have to reduce it down. So locally, it would be 1 to 24,000. So 1 inch on the map represents 24,000 inches on the ground. Now this, it's not unit specific. It doesn't make any difference what the unit is. One of that unit equals 24,000 units on the surface of the Earth, be it feet, miles, kilometers, millimeters, centimeters, whatever. You don't have to convert anything. It just means one of these equals 24,000 of these on the surface of the Earth. It's that simple, okay? Now you can write it out. I can just tell you what it is. Write it on the map. 1 inch equals 4 miles. Now this is blown up, obviously, but that's what it would be. From here to here is 1 inch. So that would be 4 miles, or 1 to 25,000, which is the representative fraction, or I can show it as this little graph. And on the map, here to here would be 1 inch, and it would be 4 miles. Okay, or if I'm doing it in kilometers, would be a little bit more, or 1 inch would be a little bit more than 5 kilometers. Okay, so written, representative, or graphic. Now, 1/24,000 is what we call large scale, because the objects appear larger, so the map is less abstract. And a scale of 1 to 50 million is small scale because the objects appear smaller, so the map is more abstract. This number might look bigger than this, but remember, this number might look bigger than this number, but remember, this is a fraction, so it's 1 over 24,000 is larger than 1 over 50 million. Okay, so large scale, less abstract; small scale, more abstract. This is important again because when you're looking at the maps in the book, you need to know the scale of what it is you're looking at. You know, how much of the Earth's surface you're looking at. And this is in the book, so make sure you pay attention to this. Notice it changes, basically in half every time. Well, at least for the first three. Basically 1 to 100 million to 50 million to 25 million down to 1 to 1 million. So notice here, Montreal is just a dot, but here, that's all you're seeing is the whole city. So we've zoomed in. Small scale, large scale. More abstract, less abstract. So you get more detail with the large scale. Okay? So again, the book uses all different kinds of maps, so just make sure you know what it is you're looking at. There's different projections. You all know what a globe is. It's the only true representation of the Earth in terms of distance, direction, area, shape, and proximity. If you take the three-dimensional sphere and turn it into a flat two-dimensional map, you're going to distort at least one of these. And remember when I was talking about how distance between degrees of longitude decreases from 111 to 0 as you get to the pole, so you have to fill in these spaces. That's what people did when they did that. They just, if it was over land, they added land. If it was over water, they added water. But notice what happens. Here's the equator. So you have to fill in all this area, so Greenland becomes significantly bigger than Africa, even though in reality it's only a tenth the size. But it keeps the longitude, the points are exactly accurate. That's no problem. So what we've done, though, is changed area. We've distorted area by using this, and this is what we call a Mercator projection. It's one of the most famous. So the projection just reduces the spherical globe onto a flat surface, and it keeps the grid system intact. It just changes it a little. Notice on this one, everything's at right angles. Now, of course, it's not that way on the globe. There's different classes. Again, this is in your book, and there's questions on the test about this, so make sure you know the three of them. Cylindrical, conic, and planar are the most common. So think of it this way. Here's the three-dimensional globe. Put a light bulb in it. Wrap a piece of paper around it like a cylinder. Turn the light bulb on, and it will project this information onto this piece of paper. And then when you unroll it, that's what it looks like. But remember, you've distorted these upper latitudes because you've added area, either water or land. If all I wanted was, say, like the northern hemisphere, for example, or, particularly the United States, I might use what we call a conic projection. And it has a standard line, which becomes the equator for that projection. And it's just wherever the cone touches the Earth. In this case, I can't really see it. What is it about? Right around here, so the standard line. And it has two standard parallels, one above and one below. But so it's accurate, really accurate right around here, and then it distorts it a little. But notice what it excludes. You don't see anything of the southern hemisphere because the cone only covers this. If I want to look down and just see the northern hemisphere, I just touch right here. I just put the map or the piece of paper right on the North Pole, turn the light on, and so I get the Northern Hemisphere. Now, commonly, map projections are a combination of these. It's a compromise, and this is like the most famous. It's what we call an oval projection. Nobody lives in Antarctica, so we exclude most of that. Nobody lives in the North Pole, so we exclude some of that. The rest of it's pretty accurate. So this is a Robinson projection. It's what National Geographic uses. So again, this is in your book. You know, at least know the basics. We're not in the lab class. We'll spend some more time on this, but for here, just, you know, the book uses all different kinds of projections, so it's important to know, you know, what the scale is, what the scale is, and also what kind of projection. There's the Robinson projection right there, an oval. It's a compromise. The higher latitudes are exaggerated less than they would be in, say, a Mercator. See, here's Greenland, and here's Greenland. So Greenland's a little closer to its real size. It's not as big as Africa, or bigger than Africa, than it was in the Mercator projection. Now, you know, let's take a break here, and then I'll get back and we'll finish up with remote sensing.